开始上课啊。Okay, let's continue our course. Okay, today is April April 15th. Okay, but there are some we still have some materials not finished yet. Okay, for the dynamic analysis topic. So let's go back to topic 11. Okay, but before I start. Go back to topic 11. Okay, let's see what we discussed. Okay, 你说你要那个对。Okay, let's talk something more about sequences and time series and okay, let's take a look. Okay, when we talk about sequences, okay. Actually, it has several different manners, different types of data to be analyzed. So we can roughly categorize those different types of sequences. Okay, the first one is called time series. Okay, what is time series? It looks like this one. You have time right here, and there's your value. Okay, with different times. For example, stock. Okay, for example, stocks. Okay, for example, that's Apple. Okay, the price of Apple, and we have another. For example, Tesla. Okay, for such kind of data, okay, we have time for time t0, t1, t2, and usually so on and so forth. Okay, so we have such kind of data. Okay, for each different time point, okay, we have different values. Okay, so usually we like to do some prediction, right? We like to know what is the next value of the Apple's price at tk or tk plus 1. It is one of the data type, okay, which we call time series. And how do we analyze such kind of data? Okay, like what we introduced before. Okay, we have Apple, we have Tesla right here, right? We have two different data to be modeled. Okay, and usually, okay, time 0, time 1, time 2, time 3, time k. Okay, and usually we can write it in this way. The y value is exactly the value we like to predict, k plus 1. So you have k features, and you can use these features to predict next value. Okay, there are several different methods, okay, ways to do such kind of prediction. That's one of the way to do such kind of things. However, there is another type of data that we call event sequence. Okay, it is a little bit different from time series. Okay, so for example, we have an a sequence, okay, called sequence A. Okay, and it looks like this. Okay, at the first place, okay, some event happen. Okay, for example, A, and next one A, next one B, C, D, A, C, E, something like that. Okay, you can write it down. Okay, we have another sequence like this. Okay, sequence B. Okay, and of course there are several different events. Okay, sequence A and B may share those events or may not, which we don't know. But usually, okay, for example, A, C, D, A, C, B, E, and so on and so forth, something like that. Okay, Of course, we can view, okay, we can view those events as a value and write it down, okay, and use a similar approach, similar method to describe such kind of sequence data, okay, just like what we did on time series data. However, usually we do not, usually we don't think it is proper to usually we don't think it is proper to model event sequence data by using the table, because okay, that is because okay, that is timeline, right? Timeline, okay, and for sequence A, okay, at a certain time, for example t0, okay, event A it happens, okay, and maybe at next time point event A again, okay, and maybe at time 2, time 3, okay, there has no event, and next it is B, okay, maybe C, D, and so on and so forth. Because every time when you try to observe, okay, your subject, for example, that is sequence A, it is not necessary you can observe an event and it is happening at this time point. So sometimes when we talk about event sequence, so sometimes when we talk about event sequence, okay, some event might happen or some event might not happen. Okay, so there's another problem like this. Okay, of course it's time, and there's sequence B, and we have the same time. Okay, and okay, I use the green. Maybe the first event is exactly happens. Maybe the first event of sequence B is exactly the same time. Sorry. Maybe the first event of sequence B is exactly happens at the same time as the first event of sequence A, which is A. Okay? Maybe the second one is the same, but maybe it looks like this. So it is not proper for us. Okay, we say it's not proper. It is not proper for us to model such kind of sequence data by using the table at the right top side. Okay, because for each feature, it does not reflect the time relationship of event happens in sequence A and sequence B, because it is very easy to understand, right? At time 2, you did not observe any event at time 2 for sequence A, but there is an event. Okay, so if you really want to model such kind of sequence data, event sequence data, by using a table like this, okay, maybe you should consider padding. Padding means you simply put a specific event, for example, right here, and that means, for example, empty pad. Okay, it has a different name. Now, that means, okay, I manually, 就是我人工的哈 insert a null event, an empty event, a padding, okay, at the place which you observe sequence A, which is time t2, so that you can align 就是对齐哈 you can align those different events. Okay, So that's one of the way. But usually we don't do this. Usually we don't do this. A more appropriate way to describe sequence event data is what we introduced last week, one-hot encoding. Okay, how do we make one-hot encoded table, right? That is sequence A and sequence B. Okay, first you have to write down how many events are in this system that you can observe. Okay, for example, you can observe event A, B, C, D, E, and maybe you have even more event type. So that is your features. Okay, so one of the way to describe A is that you simply just count okay, how many events, okay, in sequence A. Take this example, okay, observe 3 A's in sequence A. So you write down 3 right here, and we have 1 B, 2 C, 2 D, and 1 E. So that you can use this simple by counting. Okay, that is one of the by counting. For event B, 3, 1, 2, 2, 1. Okay, and so on. Okay, that is one of the way. Okay, the other way is that like this. We don't do counting because the length of because the length of sequence A and length of sequence B may not exactly the same. Okay, so sometimes sequence A is longer, sometimes it is shorter. So by counting, sometimes we don't think it is proper to describe a very, very long sequence compared with a very, very short sequence. Okay, so usually, okay, when we do one-hot encoding, okay, we simply just write it down. Does this event happens? Okay, so you write down one. So maybe we can have one more event. Okay, so we just write down. Okay, in sequence A, there is one or more event A happens. So basically, it looks like this. Okay, and for event F, okay, it does not happen in the sequence A or sequence B. So we write 0 right here. Okay, so that is usually we use these things to use one-hot encoding to describe such kind of data. Of course, you can see that from the perspective of maybe expert. Okay, AABC and AACD, that they are not exactly the same. However, after one-hot encoding, they looks like the same, right? Because they are all 1, 1, 1, 1, 1, and 0 to describe sequence A and sequence B. But so it depends on your domain knowledge, okay? Which if you want to do one-hot encoding, okay, counting is better, or you use a binary value, okay, 1 and 0 to describe this data is better. It depends on you, okay? And also, okay, there's another. When we say counting, usually, okay, that is another term to describe such kind of one-hot encoding called frequency, right? How many times this event happens in this sequence, okay? However, there are another way to, it's called rate, okay? So for example, for sequence A, okay, there are 9 events, right? 9 events in this sequence. So sometimes when we talk about, we use one-hot encoding to describe a sequence, but we use rate to describe it. So sometimes we can divide it by event. Okay, maybe for sequence B, there's another. So it has 10 event, right? Events. So it divided by 10. And of course, we have one more. Sorry. Something like that. Okay, so that we can convert, okay, time series or event sequence by using a table. So if we have such kind of table, then we can apply the algorithm we taught before, okay, SVM, the logistic regression, linear regression, something like that, to help you to do such kind of analysis, okay, no matter what kind of Y you want to do, you want to predict. Okay, that's another way to describe sequence data. Okay, and next, okay, there's some notice. Because for time series or for event sequence, there might be a lot of events happening in the sequence. So maybe, okay, there's some problems. For example, too many event. That means, okay, we simply just use A, B, C, D to represent event, right? So maybe there's a sequence that it contains, for example, too many features. For example, as we mentioned before, if you want to describe malicious software by using dynamic analysis, and you describe the malicious program by using the Windows API calls that it invoked it. So how many Windows API calls in Windows system? We mentioned it before. 30,000 or 30,000. It depends on the libraries you use. So there are too many events. So your feature will be large. Okay, so it looks like call 1, call 2, call 3, call 3,000. Okay, call 30,000, something like that. So your feature will be very, very large, and that is what we don't want to do. So if you have too many events, too many features, okay, there are several we say mechanisms that can help you to shrink the size of the features. Okay, so first thing is you do dimension reduction. Okay, that's exactly what we told you last week, is principal component analysis. You can use principal component analysis to shrink your size from X to which dimension is maybe maybe that is only K dimension. Okay, K dimension. So you can use principal component and select a K to reduce your features from 30,000 dimension to maybe 300 or whatever you'd like. Okay, you can do dimension reduction. Okay, the other way is to manually UAL. Okay, manually. Okay, select manual selection. What does that mean? That means for a specific feature, okay, for a specific feature, and you take a look at this column, okay. Now, of course, there are several different samples right here. Okay, you take a look at this specific column, okay? And further, you can do some calculation, right? If the average of this column and the standard deviation of this column, for example, if the average is quite low, which means, okay, among all those n samples, only a few or very few samples they use this feature, which means it's 1, right? Because we say if we do counting, okay, the average number is very low, and the standard deviation is very low, which means only very few sample write 1, okay, in this column, and most of the samples do not use this event or this feature. So basically, you can set a threshold, okay? Consider how many n's you have. Okay, maybe you can say, okay, if n is 1,000, okay, but only maybe 2 of the samples, 3 of the samples, or even 5 of the samples, they use, okay, they have such kind of event, C3000. Then you can consider manually remove such kind of event, because in this column, most of the value in this column is 0. Okay, so sometimes we describe such kind of scenario by sparse。 sparse 就是空洞的意思，就是有点空的意思啊，就是大部分人都是零嘛，那只有非常少数的人在那个栏位上填上1嘛哈。So if it's a sparse column, so you can remove such kind of columns. Okay, such kind of columns. Okay, so that's one of the way. Okay. So I think that's enough. Okay, so let's go back to topic 11. Okay, and one more thing. Okay. Some mathematicians, okay, they believe that if you use one-hot encoding, okay, like this, okay, you simply just count or calculate the rate, or simply calculate a sequence, use this event or do not use this event, right? So some mathematician believes that you miss some information, especially, okay, the relationship of order 就是有些数学家认为说，如果你用 one-hot encoding 的话，你会丧失掉一些讯息，那些讯息大部分是跟 order 就是顺序是有关系的，对不对？我们这边说sequence A 有2个 A 嘛，它是连续的2个 A 啊，可是你在那个表格里面，无论是3/9还是3，还是下面这个 one-hot 是写成1，你都看不出来 A 有连续2个的这件事情，对吧 ？Okay, so that for such kind of event sequence, okay, there's another problem. Okay, so that is problem number 2. Missing order information. Okay, so there's a simple way. Okay, of course there are a lot of different complex way to deal with order problem, but there's a simple way, what we call Ungram. What does that mean? Okay, if we say 2-gram, that means when we encode, okay, 2-gram, when we encode the table, okay, we do not simply use A, B, C, D, E, F to encode, to do one-hot encoding, okay? Rather, 2 means we do pairs, okay? The first feature. Okay, the first feature is A, then AB, AC, AD, AE, AF. The next one is BA, BB, so on and so forth, until the next one is FF. Okay, so the new table, what we call 2 gram 1 hot. Okay, it is a 2 gram 1 hot table. So you can simply just take a look at the sequence A. Okay, it should be look like this. So AA, okay, simply write it down. AB, okay, AA is right here, AB is right here. AC is right here. AD, no, no, we don't have AD. We have DA, but you have to write it in the other column. AE, no. AF, no. BA, no. BB, no, and so on and so forth. FF, no. So you can use a very simple 2 gram 1 hot table to describe the original sequence, which can preserve, okay, a little bit information about the orders of the original sequence. OK， 就是如果我们用 2 gram 1 hot 的形式来描述原本的 sequence 的话，这样子我们可以保留比较多有关于先后顺序的事情啊。那你用英文好。And further, can you use 3 gram, 4 gram, and so on and so forth? Of course, you can use it, but you have to think about one thing. If you use only 1 gram to describe such kind of data, okay? We have only 7 events, right? We have only 6 events by using 1 gram 1 hot, but for 2 gram 1 hot, okay, the size of the feature should be 6 times 6. We have 36 different 2 gram features, okay, to describe this data, and 3 gram would be this one, and so on and so forth. So your feature will increase, okay, exponentially. So basically, you have too many features to describe this sequence, just because you want to preserve the order of the sequence event. So basically, if you apply 2 gram or 3 gram, we strongly recommend you consider using some dimension reduction techniques like PCA after you do 2 gram or 3 gram. Okay, so that you can decide which kind of mechanism you'd like to use. Okay, so basically look like this. Okay, let's go back to our topic 11. Okay, so basically, okay, we like to construct a table, a 1 hot 1 gram table. Okay, so basically I provide that's it right here, and I said, okay, I would like to use 1 gram. Okay, so first you have to count how many different types of event you have. Okay, for example, it has 10 different types of event. Okay, so 11 types of event. Okay, indexed from 0 to 10. Okay, so we have different events. And further, okay, you should count how many. For example, we have 31 samples right here. So the table looks like this: 1, 2, 3 to 31. Okay, so we have 11 events. Okay, x0, x1, 2, x10. Okay, then x1, x0 means create, process, internal, and so on and so forth. So basically, your table looks like this. Okay. When you go home, okay, take some time to look at the code. Okay. We are trying to make a table look like this. Okay. So basically, okay, the table. Okay, I will show you right here. So we do one hug right here. So for this sample, okay, it did not invoke this create process internal Windows API call. When we that is a malware sample, right? When we analyze this malware sample, okay, when we do dynamic analysis, this malware sample does not invoke this Windows API call, so we do not observe such kind of event. So we write 0 right here, but it indeed invoke reg delete key, okay, and so on and so forth. So basically, we can use one-hot encoding to describe different malicious software by using Windows API call as features. Okay, so that is a table. Of course, it is a table, so we can do some calculation. Okay, for example, how many samples have invoked this specific Windows API call? So basically, it is the average right here. The summation. That is 14, 31, 31, so on and so forth. Okay, the table is like this. So basically, okay, you can observe that some features like this, they are useless. That is because every malicious software invoke, for example, regis query value, this Windows API call. So this API call does not have any capability to differentiate this 31 malware sample. So this column is useless. Okay, if you use one-hot encoding to describe those malicious software sequence, API call sequences. So basically, of course, there are several different ways to help you to analyze this data. For example, you can convert this table, okay, from one-hot encoding 1 gram to one-hot encoding 2 gram. So that will enrich your table, your columns. Okay, so you can reduce the number of columns like every malware have invoked such kind of libraries. So basically that's it. So that is okay. So as we mentioned before, if you have too many features, too many events, okay, to describe your sequence, you can perform principal component analysis. It's one of the way to do dimension induction. So here's the code. Okay, make sure you follow this code. Okay, when you do your homework or at home. Okay, so basically you can where is it? Okay, right here. Basically, okay, the parameter I set right here is 2, which means in total we have how many? In total we have 11. Like this, right? 1, 2, 3. That is original table, right? We have 11, but I would like to do a principal component. So here is a principal component analysis, right? And we have a new space, and we make a decision like right here. I would like to cut we only preserve the first 2 dimensions after we do principal component analysis. So we reduce our space, our dimension from So from the original, how many we have? Oh, 0 to 10. Okay, so that is 10. So the original dimension is 11, right? So we convert it to another space which has also 11 dimension, but we cut it to only 2 dimension because I said it right here. So we only preserve the first 2 dimension after dimension reduction. So basically, since we have only 2 dimensions, so we can draw the value, okay? By using the new PC1 and PC2 as the coordinate. Right, so point is right here. And we can see that, make sure you understand this one, it's the line number 9, okay? I print something right here, okay? That means, okay, the variance of the first 2 dimension, okay, its ratio is 73% and almost 19.7%. Oh, sorry, it should be like this. That means the first 2 dimensions after we do dimension reduction, okay, the summation of this variance is 91%, which means all of the information, 91% of the information has been compressed to the first 2 dimensions of PC after principal component analysis, which means it is good enough to use only 2 columns, 2 features, 2 principal component 2 principal components to represent the original 11 dimension data. Okay, that is good enough. So we use these things, okay, to simplify our analysis. Okay, so that is. So as we can see that originally we have 31 points. Right, we have 31 points. However, as you can see that there are only very few data points right here. The darker color means there are multiple points has been plotted on this point. Okay, the lighter one means maybe only 1 or 2 data point has been plotted in right here. That means among these 31 data points, okay, some of them will be at the same coordinate points if we use PC1 and PC0 to represent this data point. 中文是说我们原本有31个点嘛，对不对？但是你现在看到这上面点有深有浅嘛，比较深的点就是比较多的点被印在同一个点上。那也就是说呢，如果我们只用 PC0 跟 PC1 去描述这些点的话，它们会被点在同一个点上，在这个新的平面上啊 ，PC0 跟 PC1 平面上。那也就是说呢，其实原本的资料集31个点，然后11维呢，有某些点呢，如果我们以2维的角度来看，它们是重叠的，也就是它们是不可区分的啊，大致上是这个样子。那原本31个点嘛，但是上面看起来只有大概6个东西左右，而且你可以稍微分一下群哈，就是说这边可能是一群啊，这个可能单独一群啊，这2个可能比较近，所以它们是一群。Okay, and sometimes you can simply just do some cluster, okay, to cluster points which are close to other points. Okay, so that means from the perspective of principal component analysis, okay, these 3 data points are quite close, which means their one-hot encoding are related similar to each other 啊，就是说，如果我们在这个 PCA 平面上能够做出这样一群一群的东西的话，我们会认为说这3个点呢，就左上角这3个点，在 PCA 的观点上它们是相近的，而在 PCA 的观点上相近的，他们就反过来的意思就是说，他们在原生的那个11维里面，他们那个one hot的那个数值啊，0101的这种数值啊，应该也是相近的。 那也是相近的话，我们就再往回推一个，也就是说，它们的 sequence 使用这些 event 的数量应该也是相近的，所以我们就认为那些 sequence 会比较相近。但是我们刚刚讲了一个缺陷这个是在不管任何顺序的情况之下，我们认为它使用 event 的次数，不是次数啊次数要 frequency， 我们认为它使用这个 event 的情况，就是1跟0的情况，这3个点应该是相似的。好，那你就会问说，这只是使用的情况嘛，就是1010的情况嘛，这3个点是相似的。还有左下角那可能有2、3个点，不止哦，这可能有7、8个点塞在那个左下角那个点上，因为我们总共有31个点是相似的。那如果你说我不想要用使用的情况来描述 sequence 的话，那接下来你就做 2gram、3gram 嘛，因为 2gram 跟 3gram 我们刚刚讲过，你可以稍微的保留一些它的顺序关系嘛，对不对？稍微保留一些顺序的关系。那你可以用 2gram 再做一张新的表，然后因为 2gram 的 feature 又太多，对不对？所以你再用 PCA 去压缩一次到一个你满意的维度为止，然后你就再画一次到一个2维的平面上，那你再看看这个2维平面上它的 variance 大概高不高？如果高的话，你就在这个2维平面上再做一次类似像 clustering 就我们现在眼睛看到这个 clustering 的事情，那么你就会发现说，那在 cluster 内的那些点点，他们在 1 hot 2gram 的情况之下，他们的那些010的数字是相似的，对不对？所以翻过来，他们在 sequence 上大概也会是相似的，因为你保留了一点点 order 的关系。如果你觉得 O 的关系要更强烈，没关系，你就做 1 half 3gram、4gram 就一直往下做，好吗？那终究你就会发现这个方法应该是可行的你可以选择一个适当的 gram 的长度描述你原本的字串描述你原本的 sequence 的内容。然后呢，可能因为维度太多了，所以你做一个 PCA 的压缩，然后压缩到一个你适当的 K dimension。然后这 K dimension 之前包含了足够多的 variance， 这个我们上礼拜解释过那足够多的 variance 呢，就画成图，然后试着做看 cluster。那 cluster 内的人就表示他们在 PC0、PC1、PC2、PC3 上看起来是相似的他就 infer 他们在原本的 1 half， 比如说 3gram、4gram 上看起来是相似的，他就再倒过来，他们在 infer 他们原本的 sequence 的排列可能也是相似的。它虽然看起来有好几个步骤但是我们现在很多时候处理 sequence data 就是这样做的，好吗？好，那我们就先暂停在这边吧。Okay, we stop right here. So please come back in 10 minutes. Okay.